Hi, my name is Byung-cho Choi, an emeritus professor at KNU, Gyeongbuk National University in Korea. I'm the author of this book, and I'm running this YouTube site. And recently, I posted 28 videos regarding on the dynamics and control of PWM converters and the content, technical content, and all the lecture slides were based on this book. Now, I'm planning to renew this site in a more organized and reviewer-friendly format. And for that purpose, I divide the content of this book into 20 topics shown in this lecture slide. So we have a list of topics, and the previous lectures belongs to these three topics. Topic number 1, number 4, Buck converter, and topic number 6, frequency response, and topic number 7, closed loop performance. In those lectures, we analyzed the performance of PWM converters, and we predict the closed loop characteristic of PWM converters using the frequency response concept adapted to these PWM converters. To support the validity of that analysis, we need to derive the small signal model of PWM converters, and this lecture series will deal with that topic. And eventually, I'd like post all the lecture slides of these 20 topics. That will be my final goal in my career in power electronics. And so the topic 8, of course, this topic deals with the modeling of PWM converters. So let me explain the purpose of the modeling. This shows the functional diagram of PWM converters. So it consists of a power stage and the PWM block and the voltage feedback circuit. This power stage can be any one of these PWM converters, maybe one of not isolated converters, or any of isolated converters. And this is the PWM block, and this is the voltage feedback circuit employed to regulate the output of this voltage at a fixed value. This converter is known as time-varying nonlinear system, which is difficult to analyze and even more difficult to set up the control design strategy. Two main challenges in the dynamic analysis and control of PWM, these converters are: first one is time variance in power stage dynamics. Because of the presence of the switches, the configuration on the dynamics of power stage will be changed constantly in a periodic manner, so can be considered as time-varying system. And this PWM block is the typical nonlinear process. The input of this PWM block is continuous signal, and the output of this PWM block is digital signal, switch drive signal. So we may apply the averaging technique to obtain the average power stage dynamics. So we will be using this, and to deal with this nonlinearity in PWM process. And there will be the additional nonlinear relationship which will come up during the averaging process of this power stage. For example, two time-varying variables will be multiplied together during the averaging process, and it generates another nonlinear relationship. So we should average all the nonlinear relationship existing in the power stage and controller. And for that purpose, we'll be using linearization technique for the nonlinear to deal with nonlinear relationship. The purpose of this PWM converter modeling is very concise and precise. As I wrote down here, the purpose is to establish a systematic method to describe the dynamics of nonlinear time-varying DC-DC converters using the terms and format that have been used for linear time invariant system. In particular, this frequency response characteristics will be playing the major role in the analyzing and setting up the design strategy of these PWM converters. Okay. If we achieve this goal, you can freely use all the techniques developed only for the linear time invariant system, such as transfer function and Laplace transformation and Bode plot and Nyquist, Rutherford, so on. Okay? So the purpose is very simple. You want to change, you want to modify into the small signal model format of the PWM converter so you can analyze its dynamics and establish design methodology using the technique we already studied in the past for the linear time invariant system. That is our purpose of the modeling PWM converters. So this slide describe the detailed steps of PWM converter modeling procedure. Again, this nonlinear time varying PWM converter is here, and we divide it into three sub-components. One is power stage, and one is PWM block, and the other one is the voltage feedback circuit. So we'll be using three major techniques to deal with this. Okay, starting from here, our eventual goal is to obtain the S-domain small signal model of PWM converters. For that, we'll be using averaging technique and the linearization technique, and we will set up AC equation for the sum case. For example, this power stage is nonlinear time varying. This is time varying system, and we'll average this time varying dynamics to obtain the averaged dynamics, time averaged dynamics of power stage, and we will have the averaged power stage model. So this model is time invariant, but there is still nonlinear, because during this process, some nonlinearity between circuit barriers will come up and will be embedded to this model. So then we'll be using linearization process to obtain S-domain small signal model of power stage. For this PWM block, we will set up the average equation of PWM function, and this function will be linearized, and we'll have a linear modulator gain, which is a constant. Finally, this voltage feedback circuit, we don't need to average or linearize this part because this is the already linear part. Then we will set up the AC equation, and the resulting equation is called voltage feedback compensation. So now we have three small signal models: S-domain small signal model of power stage and modulator gain for this nonlinear PWM block, and the voltage feedback compensation for this voltage feedback circuit. So we combine them together, merge them together, then we will get S-domain small signal model of PWM converters, and we'll use all the existing technique for the nonlinear time invariant linear system. Okay, then using that technology, we'll analyze the dynamics of this converter and formulate the design steps of the controller. So that is the final goal of this lecture series. So converter modeling can be classified into two steps. And first one is average modeling of power stage. This is important. And if this is achieved, then will take the step of small signal modeling of PWM converters. So this consists of 2 lectures, power stage averaging and the concept of PWM switch. And in this lecture 2, we will get the average model of PWM switch and some concept of continuous duty ratio. With that, we will follow this 8 lectures. Finally, we obtain the universal small signal diagram applicable to all PWM converters, non-isolated converters and isolated converters, and operate in CCM or DCM. That is our final goal. So now we start the lecture 1, and lecture 1 deals with power stage averaging and PWM switch. Okay. First, we'll discuss the basics about this power stage averaging, and we will define the PWM switch. This illustrates the steps of the modeling of power stage. So this one is averaging, and this one is linearizing, and there is additional step which is S-domain conversion, which is very simple. Okay. Initially, we have this nonlinear time-varying power stage dynamics, and we take the step of averaging, then we'll obtain nonlinear average model, and this model can be used the time domain simulation with small and large disturbance. In the past, this was very useful because in the past, the simulating the closed loop converter is challenging task, okay, because the limitation of simulator. But now there are so many strong simulator, PSpice and ORCAD and Simplis, so on. So this is the very easy job now. Okay. So use of nonlinear average model for this purpose is not popular now, but this step is much more important. If you have the nonlinear average model, then you adapt the linearization process to obtain the linear time small signal model of power stage. This will be predict average time domain dynamics of the power stage if disturbance is very small. Okay, but also this is the application of this is very limited. Okay, and the more important passage is this one. So this is a time domain small signal model. So we convert these things to S domain small signal model, frequency domain small signal model, which is extremely simple step. Just to replace S with J omega and replace L with SL and replace the capacitor with 1 over SC. Then we obtain the small signal model of converter, and from this small signal model of power stage, we will obtain the transfer function of power stage, which are very critical to analyze the dynamics of converter and to develop the design procedure for the closed loop converters. All right, then let me explain some details about the steps of averaging and the linearization. And this shows the averaging steps employed to remove the time variance from the power stage dynamics. This black curve is current waveforms of actual buck converter obtained the cycle by cycle simulation using switch model. So this is the actual response, and this averaging procedure will produce some model, averaged model, which generate the trajectory of time averaged curve of this actual cycle by cycle triangular waveforms. Okay, so this is the exact response of switch model, and this blue curve is the response of average model. So it closely predicts the envelope of these actual waveforms, except for this ripple component, which we already know if we want, we can reconstruct this to obtain the exact response of this inductor current waveforms. So this averaging will generate some model which can generate this blue curve. That is the averaging procedure. And the second one is linearization. Linearization is to approximate a linear function into a linear relation under small signal assumption. This is very critical. When we are talking about the small signal model, this small signal assumption is all around us. In small signal assumption, you are assuming something is much, much smaller than the other thing. Something is AC component of some variable, and the other thing is DC component of that circuit variable. Okay? So let me explain this first. Okay? This is the buck converter case. Output voltage of buck converter is duty ratio times input voltage. We are assuming this is the time varying function, output is time varying function, and duty ratio and input voltage are also time varying function. So we have product of two time varying function, then this output becomes nonlinear. So we have a nonlinear relationship here, and this is another example. This is the assume this is in the diode current of boost converter, and the diode current of boost converter is product of this 1 minus dt, which is d prime t, which is time varying function, and this inductor current is also time varying function. So two time varying variables are multiplied together, and this is also nonlinear relationship. Okay? And this illustrates the concept of linearization. So this is the input and this is output. Okay? So input and output is related by this nonlinear curve. Right? So this is not the case of this. It's something else, but it is good to understand the concept of linearization. And in this, the input variable Vi consists of two components. One is DC component here, and the other one is AC component, sinusoidal component, superimposed on this DC component, which is shown here. Okay? So we can use this nonlinear curve to have exact response of this nonlinear device. Then we extend this line segment here, and this is the crossing point of this one, and the nonlinear curve. We have another point, and using these 2 points, we can predict some behavior of the response of this nonlinear device. That is the exact analysis, but that is not desirable. Alternative way, or more convenient way, or more general way, or more useful way is to approximate this curve, maybe for this part, with the tangential line segment passing through this point. Okay? So we evaluate the slope at this operating point, defined Vi and Vo, which is DC operating point or quiescent point. Then from that slope, we set up the tangential line segment and assume this tangential line segment is the approximation of this nonlinear curve, and use this as alternative of this, and we project this AC component to like here, and this will be the output variation. Okay, that is, consider this is this sinusoidal component is input, and consider this sinusoidal component is output. Then we have input-output relationship. Okay, so AC input and AC output. Then the gain is just the slope of this nonlinear curve at this operating point. Okay, so this is the very simple explanation of concept of linearization, and this area shaded with this blue blue line is the error which will be incurred during this linearization process. So to minimize this error to an acceptable level, this value should be much smaller than this one. Okay. So assumption is this AC component is much smaller than this DC component, which is called the small signal assumption. So whenever we are talking about the linearization of nonlinear relationship, we are always assuming using this small signal assumption. Okay. Okay. This explains the averaging steps, the concept of averaging power stage dynamics. Okay. Assume this is the inductor current of the some converter, maybe buck converter, and this converter consists of this. This is split switch, and this is the A through, P through, or A terminal, P terminal, and the C is pole C connected to this inductor. So for this time period, this switch is connected to A. For this time period, this switch is connected to the P terminal. When switch is connected to this A through, then inductor current will develop according to this equation. When this switch is connected to this, then the inductor current will decrease according to this, and it will continue to trace out this pattern. So this is the exact cycle by cycle simulation based on the switch model. Okay. Suppose we developed the average model of power stage, then average model will be trace out this curve which follows time averaged version of this. So this average model will generate this smooth curve passing through the time average envelope of these exact waveforms. Okay. So in summary, the method of averaging produce the smooth waveform IL bar T that follows the time average trajectory of actual inductor current of ILT. Okay. So this concept is very simple. All right. So this illustrate the averaging process and the role of average model of nonlinear relationship. And there are two well-known average techniques. And the first one is state space averaging technique. This technique was popular in the past, maybe 70s and 80s. So many people, they used this state space averaging technique. In this technique, they averaged the state space description or state equation of dynamic system, which varies from on time to off time. Okay. So there are two different sets of state equation, and somehow they average it with some appropriate weighting factor to have one state space equation which describe this time averaged behavior of this system. Okay. This is very general, so this can be applied to any dynamic system. Right. And later, the circuit averaging technique was proposed in 80s, and it is widely used until now. This is very convenient to use because it directly deals with average of circuit variable. So we don't need to manipulate this state equation of the system, and we can easily identify the average model of some element. Okay, but use of this is limited to the circuit. Okay, because this is based on the circuit waveforms of the converter. So it can be applied you cannot apply to some other dynamic system, but this is very convenient for the power electronics because always we deal with the circuit, power electronic circuit. Okay. We'll be using this. We'll be using the circuit averaging technique. If you are interested in this averaging technique, so some description about this technique is given in my book, or there are many references about this. The past references, the Dr. Middlebrook, he proposed this method, and he published many papers, and many researchers followed his work. Okay, so there are a bunch of references about this. Okay, but we'll be using this circuit averaging technique. All right. This slide shows the description of circuit averaging technique. You can read this, but it's not easy to understand this. And for me, it's not easy to explain this to you, but I'll show the procedure in the next lecture. Once you understand the procedure, this will be understood automatically. Okay, so let me skip this, and later on maybe you will read this. But I'd like to emphasize two important facts. And the first one is we'll be applying the circuit averaging technique, and during this circuit averaging process, this linear circuit component, including R, resistor, L, inductor, and capacitor, C, and voltage source and current source, all of them are invariant during the averaging process. This means this linear time invariant circuit component can be used. It stays at the same place in the circuit diagram, and its value remains the same. Okay, so you don't have to change anything. You only change the nonlinear part of circuit component. So we have two nonlinear circuit components, which is this active switch, which is the passive switch, which alternate turn on and turn off depending on the switch drive signal. Okay, so, but these two components, so they come together as the SPT switch. Then this multiple two nonlinear circuit components can be grouped together, and they can be treated as one composite circuit component in the modeling process. Namely, we don't have to separate this, and we treat this SPT switch all together, and we develop the average model of these two components all together. Okay, just one step. All right. Okay. Next, we need to understand the structure of basic PWM converters, and to understand the definition of a PWM switch and the averaging process of a PWM switch. This is a circuit diagram of buck converter and boost converter and buck boost converter. You are using this. This is the SPT switch. It consists of this active switch and the passive switch connected in this fashion, which is this. All right. This is the active terminal, passive terminal, and the common terminal is here. And the common terminal is connected to the inductor, and this is named as I, inductor terminal. And during this time period, DTS, it is connected to A, and the remaining time period of one switching period, it is connected to the P. All right? So this is the buck converter, and this structure is common to all three converters. Okay, so it is located in this fashion for the buck converter. If you rotate this 120 degree, then this C terminal comes here, A terminal comes here, and the P terminal is here, and this becomes the boost converter. If you rotate once more by 120 degree, it becomes the buck boost converter. Okay, if you rotate once and you come back to this buck converter, so there are only three basic converters configured using this structure called the three-terminal cell, and this source and this load. This capacitor can be considered as a part of a load. Okay, so common feature of this three-terminal cell is the same in all the three converters, okay, during the DTS, which is on time period. For buck converter, this voltage is this minus this, and this voltage is always lower than this. When converter is in CCM or DCM, that means this voltage becomes positive, okay. When this switch is connected to this terminal, then this voltage becomes negative of VO, so this voltage becomes negative, okay. So that is true for the all three cases. When this is connected, this inductor voltage is this one. When this is connected to here, this voltage is Vs minus VO. VO is always larger than Vs, so this inductor voltage becomes negative. Same is true here. So for all three converters, this inductor voltage becomes positive during the on-time period. With this positive inductor current will be increasing, and during this time period, inductor voltage is always negative. During this period of time, inductor current will be decreasing for all the three converters. That means during the on-time period, this inductor is taking some extra energy from the source, and during off-time period, when inductor current decreases, it delivers to the excess power to the load, okay? So output is receiving constant power all the time, and the same is true here and here, okay? So the switching action of SPT switch provide an energy transfer from the source to load in a controlled manner, okay? And the inductor is used as the transitional energy reservoir in this power conversion process. So this is the common structure for the all three converters, and this always appears as the essential part of this power conversion, okay? That provide you the idea of the defining PWM switch. Probably the PWM switch is most important term when talking about the averaging of power stage. This is the buck converter. So you have this circuit diagram. There is a PWM switch here, and this is active passive common terminal and the boost converter. PWM switch is located in this fashion, and this is the PWM switch located in buck boost converter. This should be buck boost, sorry, okay? There is no boost converter. Buck boost converter, okay? Then we take out this, we take out this, and it has the same structure. So A is here, C is here, P is here. This is active switch and the passive switch, and the active switch is closed during DTS. Then this will be opened. When this switch is opened during 1 minus DTS, this switch will be conducting. So this is 3-terminal linear device which is operating on the PWM principle. So for this we call it PWM converter. So this circuit component is symbolized like this, okay? So actually this was SPT switch, and we renamed this as PWM switch. Yeah, same thing, okay? But it has some different meaning. So we defined IA, IC, IP in this direction, and the voltage AP is defined as VAP, and this voltage is defined as VCP, and this D indicate this switch is connected to this port during DTS, and it is connected for the time period of D prime TS. So we call it this as the PWM switch, and in the next lecture we'll be discussing the average model of PWM switch, and we'll combine this average model of PWM switch with the remaining linear circuit component part of power stage, and the final result will be average model of power stage of converter. Okay, so that is the way of approaching this. And in addition to that, we'll define the continuous duty ratio concept, which is very critical in modeling the PWM power stage. Okay, so we'll be covered this in the next lecture, and I think this is it for this lecture. Okay, thank you for your attention.